Hello, everyone. My name is Egon. I'm a researcher in Lille. I'm very glad and thankful to the organizer for inviting me for this talk, especially as I'm feeling like a newbie in this community. I'm very new to the fields, and compared to the very high quality, high science talk that we had this morning and this afternoon, I will feel like a very dumb speaker, but still, I hope you will enjoy my talk. I'm kind of the opposite side of the spectrum when it comes to this, because I'm an end user of machine learning algorithms, especially in biocatalysis. So my main focus is enzyme catalysis to perform different tasks. And I will today present you the story we have about finding the way to learn on high-throughput screening data from enzyme screening toward the seeking of new enzymes that could be useful in synthesis. So it will be a very bio and chemo-based talk. I'm sorry for this if I don't know what is your background here. The enzyme class we will be talking about today are transaminases. Transaminases are enzymes that catalyze the reversible conversion of an amine donor and keto onto a carbonyl acceptor to produce a chiral amine. And it uses a cofactor which is called a PLP, pyridoxal phosphate. Basically, these enzymes are very useful to produce chiral amines that can be found in biological active compounds, but also in polymers, whatever. And these enzymes are made of homodimeric structures, and they have this catalytic cycle, which is a ping-pong baby mechanism. It is important, I wanted to show this to you because we will use this later on during the presentation. But so the idea is that these days we are trying to find new enzymes to perform new synthesis activities. And when it comes to finding new enzymes, you have the classical possibility, which is basically protein engineering. So you're trying to start from an enzyme and you modify it in order to get a better enzyme with higher speed, yields, selectivity, whatever. And this is a very efficient method. However, this doesn't embrace what nature is capable of offering. And this is why we came with a new strategy, which is based on screening biodiversity. So the idea was, okay, in nature, there are plenty of transaminases available. Can we screen them on for different substrates that are interesting in synthesis? And for this, we went to UniProt's database and we wrote transaminase keyword. And of course, you get like 1 million sequences, which is huge, and you can definitely not screen, especially as these days producing one enzyme is about 200 euros. So it would be very, very, very expensive. So what we came up with in association with the Genoscope in France, in Paris, we came up with a clustering method. I won't go into detail, but just to reduce this, to embrace the whole diversity of transaminases available in UniProt and to produce a bank of very few, 500, 1,000 enzymes, which is in our field quite huge for the moment. So in the end, what we ended up with was mainly 3 banks of enzymes which were composed of transaminases from all the different families of this enzyme family that are available in nature with a very low identity, sequence-based, and with over 800 enzymes correctly produced in our banks. And then what we've done is that we've used a high-throughput screening platform to screen all these enzymes, again, nearly 20 substrates that are, for some of them, model substrate, and some of the substrate that are very useful for example, producing peptidomimetics compounds or active drugs. And so at the beginning, the idea was really about producing an enzyme toolbox. There was nothing about machine learning, prediction or whatever. And we ended up with a very nice data set where we had like the activity connected to each of the different sequences. We were chemists, so in total we performed nearly 50,000 enzyme assays using our liquid handlers, which is to date one of the biggest screening data sets available, at least for this enzyme family. And so we were like, okay, this is very interesting. We, of course, characterize them in synthesis to see how powerful these new enzymes are. And we had like a ton of publications on this. But the thing was, okay, now that we have this very interesting data set, can we go further? Especially as these days machine learning is popping out everywhere. And so we were like, okay, can we reuse this data set to start training new algorithms to do sequence activity relationship prediction and determination in order to, in the end, maybe try to make faster the process of finding new enzyme in biodiversity. So that was the main goal that we focused on for this last part of the study. And what we started first to do is to look at the data. And as you can see, there are very skewed data because we have, of course, in nature, not all the enzymes are working. Mainly, all of them are not working, especially when it comes to one specific substrate, which is non-classical substrate. So what we came up with is this representation of the data. And as you can see here, you have the activity, the reaction rates. And you can see that most of the enzymes were not really active on the different substrates that we screened. Still, what we wanted to see is that can we still try to learn something from these data, especially as I told you, in terms of experimental data sets, this is one of the biggest that is available yet. So what we came up with was this strategy. This is the first strategy we applied. This is a very, I would say, dumb strategy in machine learning. We have performed a very small neural network, which is based on 3 blocks, 2 that are trying to embed the characteristic of the substrate, because the enzyme uses 2 substrates, and 1 which is dedicated to the protein itself. And then we concatenate the representation into a vector, and we use a dense neural network to try to predict the activity, the reaction rate. When it comes to substrates, of course, and as it was very nicely presented earlier, you have plenty of different parameters, features to describe the substrate. You can have, like, of course, all the physicochemical properties, a molecular fingerprint, moderate, whatever. And you also can use, as it was said, the language model and on the string, on the SMILE string that you can use. And for the enzyme, of course, the first thing you came up with is the enzyme sequence, the amino acid sequence, which is basically a very long sentence with no words, but you can still find tokens. And for this, you can use, indeed, classical convolutional neural network, or maybe, why not, LSTM, for example. So this is what we started with. We tested very dumbly different classifiers, especially starting with, for example, decision trees, which were definitely not, in our case, very useful. And also, we tried to use moderates in combination with TNN for the substrates. Again, we didn't have very good result there. And this is maybe because in our case, the data are not sufficiently broad and diverse to embrace to be linked to the molecular fingerprint of the substrates. And then we tried to use CNN and LSTM to describe the different substrate and the enzyme. And we started to have some success here with when using CNN for the substrate. We obtain a RMSE value of 0.019, which starts to be quite correct, at least for the classification problem. So what we've done is that we first divided all the activities into 4 classes to make the thing easier. And when it comes to classification, we have correct results. But when it comes to regression, then here the problem starts to arise because we have very bad results on regression. And we also tried to do the same with only LSTM on the SMILE string, describing the molecules, the 2 substrates of the enzyme, and also the protein itself. And here the results are lower. So we were like, okay, this is definitely not the best way to go. So as a conclusion of this very first strategy, we were like, okay, CNN is capable of extracting some feature from the sequential data, and LSTM seems to be efficient for protein analysis. But we are not very satisfied with the result we have. We have like a very, very rough first potential screening system, but that's definitely not sufficient. So why not trying to use 3D structure? Because as you've heard, Alphafold is a new revolution in our field, especially in my field, because before we were like blind when it came to enzymes. We usually had the sequence, but nothing else. And now we can with a snap of fingers, get the 3D structure of the protein and see if we can have like the relationship between the substrate of this enzyme and the protein itself. So why not trying to build a protein substrate complex 3D structure and to embed it using graph neural networks? Sadly, Professor Liu, I think, has left because I found his talk very, very inspiring. Because basically this is everything that he has presented. So the question was how to come from the enzyme sequence to the network representation, representing the interaction between the substrate and the protein. Of course, we started by performing the 3D prediction of the transaminase structure using Alphafold. And then we selected, because we are definitely not machine learning developers, we selected one first tool, which is P2Rank, which is based on decision trees to find the active sites of the protein. So when you have a protein, I don't know if you are all familiar with enzymes. So proteins, they can have active site where the chemistry happens. And these active sites are usually described by a pattern, which P2Rank is able to find. Especially if you have some insight on the chemistry that happens in this active site, it's very easy for you to teach P2Rank where to find the active site based, for example, on one specific amino acid that it requires to perform the reaction. In the case of the transaminases, this amino acid is a catalytic lysine, which is mandatory to perform the reaction because it binds to the PLP cofactor. And using P2Rank, we could just very rapidly screen the entire banks that we had to find the most probable active site of the different enzymes. And then we were, okay, now we need to dock the cofactor and the substrate onto this active site to see the relationship between the enzyme and the substrate. And with this, we used Genina software, which is based on a convolutional neural network. And as you can see, we had very good results when it came to docking the cofactor. So the pyridoxal phosphate is represented here. First, we tried on crystallized transaminases because we have in the protein data bank transaminases that are crystallized with the cofactor. And this was very interesting because we could see that when we performed the prediction on the location of the cofactor, it would match almost perfectly in most of the cases we tested with the crystal that we got from the PDB. And then, okay, now can we try to dock the substrate with the cofactor and onto the protein? And this is what we've done, again using Genina. First, we tried with the other version of the cofactor because, as I told you, the mechanism of this enzyme is a PP ping-pong mechanism, meaning that first you start with the amino donor and the cofactor, the PLP, and then you produce the PMP, which is the pyridoxamine, that you have the structure here, which will bind to the acceptor. And as in our case, we were more looking for the acceptors, we selected this other version of the cofactor to dock. And as you can see, we could obtain very nice docking. This is one of the most active enzymes we had from the screening. And we did some insight on the potential activity based on this docking. And it fits very well with what we can expect in terms of chemistry. What is interesting is that we, during these docking processes, we found that it is very important to have to keep flexible the pocket of the protein. Most of the studies that are performed these days are basically based on rigid structures. And in our case, we could find that keeping the active site as flexible as we can, knowing that we do not have like ton of computing powers, is very important because we could see that the residues were some of the residues were moving. especially these four, the threonine 241, lysine, which is basically the catalytic lysine here, phenylalanine here, and an arginine. And these are, what we found is that these are very important for the catalytic cycle and also for the docking of the substrate inside the active site. So it was logical that we could find some shifts in their position during the active cycle. But as Professor Liu told, when it comes to kinetics and catalysis, you also need like a time-based system, and this is why we are now looking more into time-based graph neural networks, because as you will see, when you try to now dock the combination of the pyridoxamine and the acceptor substrate, which is basically the next step in the catalytic cycle, you get another type of complex. And again, you have some changes in the pocket. And if you align the two, I don't know if you see, yeah, you see well. If you align the two docked systems, so in gray here you have the pyridoxamine linked to the acceptor, so the next step in the catalytic step, and in the catalytic cycle. And here you have the previous step where you only have the pyridoxamine unlinked to the acceptor, and you can see that everything is moving quite a lot, and this is logical because this is how enzymes work. And this shows how important you have to, you need to have all these graphs that are stacked up in order to embrace the whole complexity of the catalytic process. And here is just, yeah, I don't know if you will see very well because it's not very bright. But as you can see here, I just wanted to highlight the amino acids that are moving. And when we put them in relationship with the substrate, you can see that, for example, in the previous step, you have this phenylalanine that aligns for PP stacking with the pyridoxamine here. And when you have the next step, it completely shifts in another position to accommodate the substrate with the and the cofactor with the enzyme. And this shows that you can really have different graphs with different representation depending on the step, the catalytic step that you are interested in. So now we wanted to go further and try to use this a 3D structure to try to do the prediction. First, we started to do some network representation based basically on the distance between the atoms. So we took 2 angstrom for the covalent linkage and 6 angstrom for the non-covalent linkage, but it was not very successful. And now we are trying to embed some of the bond properties that you can find, because if you use, for example, the MoldStar package application to do the viewing of these complexes, or for example the PLIP package that is produced by the EMBL to model and calculate the interaction that you can have between the atoms, not only the covalent linkage, but also, for example, a PP interaction, van der Waals forces, whatever. You can start to improve the comprehension of your graph and help your neural network to understand better what happens in the catalytic site. In order to make this available to the community, at least my community, we are trying to produce now with the students who's working on this Jupyter notebook, so everybody can use this, because this will be my final message. But basically, it's very hard for my community to access to your tools, because usually we are like very afraid of using machine learning and do not understand most of them. And just as the conclusion and perspective, we are now trying to use the message passing methodology that was presented by Professor Liu to make the GNN system to produce the GNN algorithm that will embed our 3D structure, a 3D complex between the protein and the substrate. And this is based basically on a paper, a very recent paper from Liu, who proposed a system which is based on on spherical coordinate embedding for this. Stefan, for this embedding. And just to let you know that yeah, my message here is that it's very hard for the community of the people that are doing chemistry to get access to these tools. This is also why I tried myself to come to this very nice conference. And it would be very nice, even though we are starting to communicate a little bit better. I don't know how many people are really coming from chemistry. I mean, practical chemistry, yeah, one. But maybe not many of you are coming from chemistry or biology, applied biology. And I really push you to come to us because we need you to help us understanding how we can apply these machine learning tools towards our different systems. Just very quickly, I'm part of the RealCat platform, which is a high-throughput screening facility. And as you could see, there are nowadays plenty of data sets that are available, but usually they are made on theoretical data or papers. And based on my own young experience, basing some prediction on papers, it's a nightmare because you never know how the data are acquired, if they are done in the same methodologies, etc. So what we are trying to do on the RealCat platform is to perform very large screening in very standardized methodologies. And I guess Stefan Born, who will have a talk tomorrow, will talk about how we can move these data into open standards formats for data comparison. And if you are interested in trying some of your molecules, some of your compounds on screening, please don't hesitate to have a look at the RealCat website and to contact us. And there is also a 3D tour that you can visit using this link here. And I would really like to thank you for your attention, for your patience about my topic. And also, I would like to thank Guillaume Darlot, who's the student who mainly performed all the work here on machine learning. Thank you.